Section. Introduction. We're going to delve into the fascinating world of language models, LMs, and their ability to solve complex reasoning problems. These models can do everything from writing mathematical programs to solving scientific problems. One technique that has been particularly effective in enhancing these capabilities is the chain of thought, COT, prompting. This method breaks down complex problems into a series of intermediate reasoning steps. COT is great for tasks that require semantic reasoning, but it tends to stumble when it comes to problems that involve numerical or symbolic reasoning. To address this, researchers have trained LMs to write and execute code. This approach is beneficial because code provides a structured way to build and encode complex programs, and it allows for precise algorithmic computations. However, there are some tasks that are difficult, if not impossible, to express in code. For instance, writing a function that can detect sarcasm in a string is a daunting task. In this study, we introduce a new approach called chain of code, COC. This method enhances the code-driven reasoning of LMs. The model not only writes a program but also simulates the expected output of certain lines of code. The idea is to format semantic subtasks in a program as flexible pseudocode that can be caught and emulated by the LM. We call this an emulator, a combination of LM and emulator. For example, if the task is to count the number of times a person was sarcastic in a paragraph, the LM can write a program that calls helper functions such as is_sarcastic, sentence. The LM then makes a linguistic prediction and returns the result as a Boolean output, which is then processed with the rest of the program. The COC approach combines the benefits of writing executable code and writing pseudocode for semantic problems. It allows the LM to think in code. Our experiments show that COC can be applied to a wide variety of challenging numerical and semantic reasoning questions and outperforms many popular methods. We found that it performs exceptionally well on big-benched hard tasks, even outperforming human raters. To the best of our knowledge, this sets a new standard. We also found that both code interpreter execution and language model execution simulation are necessary for this performance. Unlike other techniques like chain of thought, which only emerge at scale, COC works well with both large and small models. We also show how COC can serve as a general-purpose reasoner via cross-task prompting benchmark. This method uses prompts from different problem families as context, providing only the structure of the response, not the solution itself. In essence, we're leveraging the structure and computational power of code and the reasoning abilities of language models to create a best-of-both-worlds reasoner. In the following sections, we'll delve deeper into the chain of code, COC, prompting, its implementation, and its capabilities. Section Summary. In this section, the authors introduce chain of code, COC, an extension to improve language model, LM, code-driven reasoning. COC allows the LM to not only write a program but also simulate the interpreter by generating the expected output of certain lines of code that the interpreter cannot execute. By encouraging LMs to format semantic subtasks as flexible pseudocode, COC combines the benefits of writing executable code and generating outputs for semantic problems, resulting in improved reasoning performance. Extensive experiments demonstrate that COC outperforms popular baselines and achieves state-of-the-art performance on challenging numerical and semantic reasoning tasks. Section. Preliminaries. Let's delve into some foundational concepts. We'll start by discussing language model, LM, reasoning. A key technique that has revolutionized this field is in-context learning. Instead of modifying the model's weights with gradients, we provide it with a few examples at the time of inference. These examples serve as a context and a format, allowing the model to mimic these examples while adjusting to a new query. This feature has been crucial in quickly applying LMs to new tasks as it can be swiftly adapted and requires minimal data. In-context learning has led to the development of methods that harness human thought processes and tools to enhance the performance of language models. We'll discuss 3 such methods that lay the groundwork for our chain of code. These methods, namely chain of thought, COT, Scratchpad, and program of thoughts, have shown the effectiveness of breaking problems down into smaller steps. COT uses natural language for these substeps, reflecting our thought process when tackling a complex problem. Scratchpad, on the other hand, keeps track of intermediate steps when simulating the output of code, resulting in an LM acting as a code interpreter. Program of thoughts focuses on generating the code itself, which is then run by a code interpreter to solve reasoning problems. Now, let's talk about our chain of code. It's inspired by how we humans solve complex problems using a mix of natural language, pseudocode, and running code, or how a researcher might develop a new general algorithm through a code-based formalism and then apply it to a problem. The chain of code has two steps. 1. Generation, where the LM generates code to reason through the problem given the question to solve, and 2. Execution, where the code is run by a code interpreter when possible and by an LM when not. In the generation phase, the chain of code creates reasoning substeps in the form of code. This code serves as the reasoning framework for the problem and can be explicit code, pseudocode, or natural language. In the execution phase, the chain of code not only generates reasoning code but also executes it. Once the code is written, we try to run it using a code interpreter. If the code runs successfully, we update the program state and continue the execution. If the code can't be executed or throws an exception, we use the language model to simulate the execution. The program state is then updated based on the language model's outputs, and the execution continues. We call this an emulator, a blend of LM and code emulator. This simple change opens up a range of new applications for code that mix semantics and numerics. The implementation of the chain of code is slightly more complex in the execution phase than in the generation phase. Our implementation is based on using Python's try and except and maintaining a program state. The chain of code steps through the code line by line. If a line can be executed by a code interpreter, it is executed, the program state is updated, and the program continues. If a line can't be executed by a code interpreter, a language model is given the program's context and generates the next program state. This emulation can also use the chain of thought to decide how to respond. The generated program state is then updated for the code interpreter as well. This sharing of program state intertwines the code interpreter and the language model simulator in a way that can be applied to any interweaving, even control flow like for loops and if statements. This continues until the entire code is run, and the answer is retrieved as the value of the variable named answer, or in case of irrecoverable errors, with the language model outputting a answer. Let's illustrate this with a brief example. The code answer equals 0. Answer plus equals is underscore sarcastic, backquote you don't say, answer plus equals 1, would be executed as follows. 1. Python would run the first line answer equals 0. And update the program state 2, answer equals 0. 2. Python would try to run the second line and fail, and thus the emulator would simulate the code answer plus equals as underscore sarcastic, backquote you don't say, by generating the program state, answer equals 1, which would be updated in the program. 3. Python would run the last line answer plus equals 1, and update the program state, answer equals 4. The answer would be received. Section Summary. In this section, the authors provide an overview of LM reasoning techniques, specifically focusing on in-context learning. They introduce three approaches: chain of thought, scratchpad, and program of thoughts, that leverage in-context learning to improve language model performance. Inspired by human reasoning processes, chain of code proceeds in two steps: generation, where an LM generates reasoning substeps in the structure of code, and execution, where the generated code is run by a code interpreter or simulated by the emulator. The program state is updated accordingly, allowing for the execution of complex reasoning tasks. Section: Chain of Code Abilities. The section we're discussing is titled Chain of Code Abilities. The chain of code, or COC, has several appealing features. Firstly, it allows us to use code in completely new ways by merging the benefits of code with the powerful semantic and common sense knowledge of language models. This makes it easier to express rules that are difficult to put into code, like identifying which foods are fruits. This ability could be useful beyond just problem solving, and its flexibility allows it to execute expressive language, such as pseudocode. Secondly, COC takes advantage of the coding capabilities of language models, which is a strong point of recent language models due to the high-quality data available. It also inherits many of the benefits of reasoning code, including the formal yet expressive structure of code and the powerful computational tools available to code. This includes simple tasks like multiplying two numbers, calculating the fifth root of 12,121, or simulating physics. Thirdly, COC benefits from techniques that reason through intermediate steps, like the chain of thought. These techniques allow the language model to use more computation when needed to solve a problem and provide more interpretability. We've observed that these benefits lead to significant improvements in reasoning performance across a variety of challenging tasks. We've tested COC on challenging problems that require different types of reasoning, such as arithmetic, common sense, or symbolic reasoning tasks. We wanted to answer several questions. How well does COC perform overall across a variety of tasks? Which types of problems does COC perform best on? How does each aspect of COC affect overall performance? How does COC scale with model size? How does COC perform as a general-purpose reasoner, with prompt examples from different problems rather than the same problem? How does COC compare with instruction-tuned chat models with and without tools? We've considered several approaches, ablations, and baselines, and we've also proposed two variants of COC with simpler implementation and slightly lower performance. These two variants try to run the entire generated code with Python, and if it fails, simulate the code execution with the emulator, outputting a final answer or an intermediate state trace, respectively. We've also compared COC against several baselines. In one, Python is used to run the entire generated code, and if the code is not executable, it is marked as failure. In another, the code is interpreted by an emulator outputting the final answer, and in another, the code is interpreted by an emulator outputting a state trace of intermediate steps. We've tested COC on a subset of challenging tasks from Big Bench called Big Bench Hard, BBH, to ensure we are solving the most challenging tasks. These tasks require semantic reasoning, numerical reasoning, and a combination of both. They allow us to study the efficacy of COC across varied problems, not just those that coding is a natural fit for. We've also introduced a new evaluation setting, cross-task prompting, where 3 examples of different problems are provided as context. This means the language model has in-context examples of the format of reasoning, but isn't provided explicit instructions on how to reason. We see this as an indicative signal for a general-purpose reasoner, which in many real-world applications would be asked to reason across a wide variety of tasks. The models we've used include the OpenAI family of models. For instruction-tuned models, we compare to recent variants of GPT with the chat completion mode run in October 2023. The results below are using the text DaVinci 003 model unless otherwise stated. Section Summary. The chain of code, COC, approach combines the advantages of code and language models to enable code use in new ways, leveraging the powerful semantic and common sense knowledge of language models. It inherits the benefits of reasoning code, such as the formal structure and computational tools, and also incorporates techniques that reason via intermediate steps for improved interpretability and problem solving. Empirical evaluation shows significant improvements in reasoning performance across various tasks, including arithmetic, common sense, and symbolic reasoning. Section. Results. Let's discuss the results of our study. Firstly, we'll look at the overall performance. Our method, which we call chain of code, COC, outperforms other methods in a number of tasks. It even surpasses the human baseline in many cases. In fact, COC's performance is 84%, which is the best we know of. In some tasks, COC performs exceptionally well, achieving nearly 100%. These tasks usually involve complex language but simple code, like a multi-step arithmetic problem. We also found that chain of thought, COT, performs better than the human baseline in several tasks, while the direct answer method doesn't perform as well. Next, we'll break down the results by problem type. We categorized problems as either primarily algorithmic or primarily natural language. COC performs exceptionally well on algorithmic tasks and equally well as COT on natural language tasks. This is encouraging because we might expect language-oriented tasks to be more challenging for code. Our method uses a language model simulator to simulate the output of code execution, which helps retain the semantic reasoning capabilities of language models for natural language problems. We also categorize tasks based on how different each question's response is and whether the code can be fully executed by Python. We found that when the code is repeated and run by Python, COC performs nearly perfectly. However, these tasks seem to be among the most challenging for other methods, including human raters. We performed several ablations to understand each aspect of chain of code prompting. As expected, the approaches that execute Python achieve 100% performance on several tasks. However, the approach that relies solely on Python performs poorly when applied to non-algorithmic tasks. We also found that COC without the Python interpreter doesn't perform well, but the step-by-step approach proposed in Scratchpad prompting improves performance in each task. We also observed that as the model size increases, the performance of COC improves. In fact, for some algorithmic tasks, chain of code even outperforms the best human raters. Interestingly, COC outperforms the direct question answering baseline also for smaller models, suggesting that it's easier for smaller models to output structured code as intermediate steps rather than natural languages. For cross-task prompting, where we prompt the language models with a few examples from different problems, the performance drops for all methods. Despite this drop, COC outperforms COT and direct prompting at scale, nearly achieving human average performance. Finally, we compared against instruction-tuned models with the chat interface. For the baselines, we asked the model to either directly answer or think step by step. For COC variants, we asked the model to write Python code to help solve the problem, if it's helpful. The COC Python baseline can be thought of as a comparison to a language model with Python tool use. With GPT 3.5 Turbo, both COT and COC Python show benefits over direct prompting, although both are strongly outperformed by COC interweave. With GPT-4, despite the considerable model strength advantage over Text DaVinci 003, COC interweave still outperforms, though the gap is narrower. Section Summary. The overall performance of the chain of code (COC) approach is superior to other methods, surpassing the human baseline in terms of the number of tasks it exceeds and the overall amount it exceeds. COC performs well on algorithmic tasks and on par with COT on natural language tasks, demonstrating the flexibility of using a language model, Emulator, to simulate code execution. Additionally, COC achieves nearly 100% accuracy when the code is repeated and run by Python, but still outperforms other baselines in different categories. Section: Robotics Applications. We're going to discuss how robotics applications can benefit from the use of code-on-code (COC) technology. Robotics tasks often require both semantic and algorithmic reasoning, as well as the ability to interact with other code-based interfaces, such as control or perception APIs, and with users through natural language. Let's take an example of a task like, sort the fruits by size. The robot needs to identify which items are fruits, arrange them by size, and then translate these decisions into actions that the robot can perform. COC, specifically the interweave version, can tackle these challenges using the Python interpreter and the emulator at runtime, while also providing more interpretability and detailed control of the robot's actions. Let's talk about our experimental setup. We have a tabletop environment with small objects like containers and toys, and a UR5 robot arm equipped with a vacuum gripper and a wrist-mounted RGBD camera. The perception API we're using is called detect_objects, which identifies objects from the wrist camera and returns a list of these objects along with their probabilities, labels, bounding boxes, and segmentation masks. This API works by first asking GPT-4v for a list of objects, and then using grounding SAM to locate them. The control API we're using is pick_place, obj1, obj2, a basic script that picks up one object and places it on top of another. We also have a text-to-speech API, say, sentence, that allows the robot to communicate with the user. We tested our setup with a variety of tabletop pick and place tasks that required semantic reasoning. We used few-shot prompting, providing one example as context so that the language model could understand the expected structure and the available robot APIs. From this single example, we found that our model could generalize to new objects, languages, and task domains. It's important to note that for these robotics tasks, our main method, COC, interweave, was the only approach that worked, as the code required a line-by-line interaction between the Python interpreter execution, robot APIs, and the emulator. Common sense QA-like is _compostable. Now, let's look at some related work. Language models have made significant strides in their abilities and applications, thanks to their overall performance and emerging capabilities, such as few-shot prompting and abstract reasoning. Several works have used prompting to improve reasoning, breaking tasks down into intermediate reasoning steps, proposing a series of increasingly simpler problems, and maintaining a trace of intermediate results for interpreting code. COC builds on these ideas, recognizing that code is a formal, structured way to break a problem down into sub-steps, offering many advantages over natural language alone. Many recent works have proposed techniques for language models to use tools to respond to queries. These tools have often been provided to the language model through prompting, enabling tools like calculators for math problems, code interpreters, databases, and more. The ability of language models to code is well known, and they have been applied as programming assistants and shown to be capable programmers on their own. This ability has been applied to a variety of tasks outside of language alone, leveraging their ability to reason through code in new settings, such as robotics, embodied agents, or vision. In this work, we focus on the interaction between writing code, running code, and language models simulating code, thus enabling new regimes of language model code applications, such as semantic reasoning.